Hello, everybody, and a very warm welcome to all of you on the excellent educational platform of Foundation Agri classes. I'm your host, and in today's special audio learning session, we are going to deeply explore a very important topic of agriculture in a simple, clear, and highly engaging way, so that your concepts become crystal clear and your exam preparation becomes truly strong.
It is wonderful to be here, and this feels like a really important one. We're getting into the nitty-gritty of soil science today, not just the broad strokes.
Absolutely. Today, we're diving headfirst into what I like to call problematic soils. And specifically, we're tackling two big ones from our source material: sodic or alkali soils, and then acid sulfate soils.
These are huge. I mean, for anyone preparing for those competitive exams, ARU, NET, JRF, ICAR, you just can't skip this. These are guarantees questions.
That's exactly right. And you can't just guess your way through them. The whole point of this deep dive is to get you beyond just memorizing a few facts. By the end of this, you should be able to, really understand the why behind it all. Why do these soils act this way? What are the specific chemical tripwires that define them?
And how to fix them.
And how to fix them, step by step. So we're covering the definitions, the formation, the problems they cause, and of course, the reclamation strategies.
I'm really glad we're doing this because I'll be honest, this is an area where the numbers can get very confusing. Trying to keep saline, sodic, and acid sulfate soils straight.
Yeah.
Remembering which one has a high EC versus a high ESP
Uh-huh.
under exam pressure, it's easy to mix them up.
It is the single most common place students get tripped up. But I promise, by the end of our session, those distinctions are going to be absolutely crystal clear in your mind. We're going to follow the material very closely. First, we'll master sodic soils and get to know the main villain, which is sodium.
Okay, sodium is villain number one.
And then we'll pivot to the coastal problems of acid sulfate soils, where the villain is a mineral called pyrite.
Sodium and pyrite. Got it. Two totally different bad guys, so I'm guessing they need two totally different game plans to deal with them.
Exactly. All right, let's jump in. We're opening up our first topic: sodic or alkali soil.
Okay, first question right off the bat. Are sodic and alkali just two words for the same thing? Are we using them interchangeably?
That's a great question. For our purposes and in the context of our source material, yes. You can think of them as two sides of the same coin. Sodic points to the cause, the high concentration of sodium.
Right, the sod in sodic is for sodium.
Precisely. And alkali points to the effect or the consequence, the high pH, the alkaline reaction of the soil. So they both describe the same problematic condition. Now, let's get technical, the definition. There are three very specific parameters, three numbers you have to know. Think of it like a checklist. A soil has to tick all three of these boxes to be officially classified as sodic.
Okay, I'm ready. What's box number one?
The first parameter is EC, which stands for electrical conductivity. In a sodic soil, the EC is less than 4 dsm. That's decisimens per meter.
Less than 4. Huh.
Mm,
That's interesting. I think most of us, when we hear problem soil, we immediately think of high salts, which would mean high electrical conductivity. But here it's low. Why is that?
That is such a crucial point to grasp right at the beginning. Yes, the EC is low, and that's because the main problem isn't a high concentration of soluble salts just floating around in the soil water. This isn't a saline soil. In saline soil, the water itself is salty, like seawater, which conducts electricity well.
Okay.
But here, the villain, the sodium, isn't primarily in the soil solution. It's stuck somewhere else.
It's attached to the soil particles themselves.
You've got it. Which brings us directly to the second box on our checklist. This is the big one. The most defining characteristic is ESP, the exchangeable sodium percentage.
Yeah.
In sodic soils, the ESP is greater than 15.
Greater than 15. Okay, let's unpack that term. Exchangeable sodium percentage. So we're talking about the cations that are sitting on the cation exchange capacity sites on the clay, right?
Exactly right. Imagine a tiny clay particle. It's negatively charged, so it acts like a magnet for positively charged ions or cations. These are things the plant needs, like calcium, magnesium, potassium. You can think of the surface of the clay particle as having a bunch of parking spots or seats.
Okay, so these are the exchange sites.
Yes. An ESP greater than 15 means that of every 100 of those seats available, more than 15 of them are taken up by sodium ions, now plus.
15% doesn't sound like that much, though. It's not even a majority. Why is that the magic number? Why does everything go wrong after 15%?
It's a fantastic question. It's because sodium, as an element in the soil, punches way above its weight. It's a really disruptive character. Even when it's just a minority shareholder at 15%, it starts to completely dictate the physical behavior of the soils. Like,
Mm,
imagine you have a well-behaved classroom of 100 students, and you introduce 16 really rowdy ones. They can change the entire dynamic of the room.
that's a great analogy. Okay, I get it. So a little bit of sodium goes a long way, in a bad way. And the third parameter,
The third parameter is pH. Sodium is the salt of a strong base. So when it's present in high amounts and reacts with water, a process called hydrolysis, it forms sodium hydroxide. This is a very strong alkali. As a result, the soil pH just skyrockets. It ranges between 8.5 and 10.0.
wow, up to 10. That is incredibly alkaline. Most plants would really struggle in that.
They would. It's a very hostile chemical environment. So let's just recap that definition because it's so important. For acidic soil, you're looking for EC less than 4, ESP greater than 15, and a pH between 8.5 and 10.
Okay, got it. EC4, ESP15, pH 8.5 to 10. So we have the definition down. But why? Why is sodium so bad? What is it physically doing to the soil to cause all these problems?
This is the perfect transition to the next part of our material, the physical characteristics. The root of all evil in acidic soil, the fundamental process, is something called dispersion.
Dispersion. Okay, I've heard that term used in contrast with flocculation. Could you break down what's happening at a particle level?
Absolutely. Think of a healthy, well-structured soil. The tiny, flat clay particles, or plates, are all bundled together in little stacks, like stacks of playing cards. This bundling process is called flocculation, and these bundles create larger units called aggregates.
And that's what creates the pore spaces for air and water, right?
Exactly. The spaces between those stacks are the pores that allow roots to grow and water to move. The element that is really good at holding those stacks together, acting like the glue, is calcium.
Okay, so calcium is the hero here. It builds good structure. What does sodium do?
Sodium does the exact opposite. It's a destroyer of structure. The sodium ion, Na plus Han, has a very thick, what we call a hydration shell. It just loves to be surrounded by water molecules.
Okay.
So when these sodium ions get onto the surface of the clay particles, they bring their big, puffy water coats with them. And these coats act like bumper cars, physically pushing the individual clay plates apart. They repel each other.
So it literally blows the stacks of cards apart.
It completely unravels the structure. The aggregates disintegrate. The particles are no longer clumped. They are floating around individually, dispersed in the water. And this leads directly to all the physical characteristics we see in the field. When that soil gets wet, it becomes a soupy, unstructured mess. It's described as being extremely sticky and plastic.
I can just picture trying to walk on that. Your boots would weigh a ton, just covered in mud.
They would. It clogs up plows and tillage equipment. It sticks to everything. It's just awful to work with. But believe it or not, the real problem starts when it begins to dry out.
What happens then?
Well, as the water evaporates, all those tiny individual clay particles that were floating around, they settle. But because there's no structure, no clumps, they settle into a dense, solid, interlocking mass. All the pores are gone. It becomes incredibly hard, like concrete.
So that's the duality they talk about.
Yeah.
Sticky when it's wet, hard as a rock when it's dry.
Exactly. And this directly causes another major problem: surface crusting. Imagine a rain shower hits this soil. The raindrop's impact instantly disperses the surface layer. The fine particles immediately clog up any remaining pores. Then the sun comes out.
And it bakes into a hard crust.
A hard, impermeable crust. This crust is a physical wall. If you're a tiny little crop seedling trying to emerge from the soil, you push up and you hit a ceiling you can't break through.
So you get germination failure. The seeds sprout, but they can't get out.
Very often, yes. And for the plants that do manage to emerge, or for the ones already growing, they face another huge challenge: a very low infiltration rate.
Meaning the water can't get into the soil.
Correct. Because all those pores are clogged and sealed, water from irrigation or rain just sits on the surface. It forms puddles and stands there for days until it evaporates back into the atmosphere.
So that's a terrible paradox, right?
Yeah.
You could be in a dry, arid region, you apply precious irrigation water, but it never actually reaches the plant's roots because the soil itself won't let it in.
It's the ultimate frustration for a farmer. The water is right there, but it can't get to where it's needed. Or you get the opposite problem where the surface becomes completely waterlogged, which suffocates the roots because they can't get any oxygen.
So either way, the roots are in trouble. They're either too dry or they're drowning.
It's a lose-lose situation. And this all cascades into the list of problems in our next section. We've got dispersion, which leads to reduced permeability and waterlogging. This causes poor root penetration. And on top of all these physical problems, you have the chemical issues.
Right, the high pH. I'm guessing that locks up a lot of nutrients.
Absolutely. At a pH of 9 or 10, many of the essential micronutrients, I'm talking about zinc, iron, manganese, they become insoluble. They're chemically locked up. They might be in the soil, but the plant can't absorb them. It's like having money in a vault you can't open.
So the plants show deficiency symptoms even if the nutrient is technically there.
Yes. And beyond that, high concentrations of sodium itself can be directly toxic to many plants, and you also often find problems with boron toxicity in these same soils.
It just sounds like a complete nightmare for farming. Low productivity is almost a guarantee if you don't do something about it.
It is. Which, of course, brings us to the most practical and important part of this whole discussion, reclamation. How do we fight back? How do we fix this?
Well, based on everything you said, the core issue is that sodium is sitting in the wrong seat. It's on the exchange complex. So I guess the solution has to involve kicking it out of that seat.
You are thinking exactly like a soil scientist. That's the heart of it. Our material outlines the principles of reclamation. There are three main goals. Goal number one is exactly what you said, chemical exchange. We have to replace the exchangeable sodium, the Na plus L, with calcium, Ca2 plus Tessac.
Why calcium specifically? What makes it so special?
Calcium is the natural hero of soil structure. It's what's called a divalent bication, meaning it has a 2+ charge. Sodium only has a 1+ charge. Because of that stronger positive charge, calcium binds much more tightly to the negatively charged clay particles. It essentially has more grabbing power. It can muscle the sodium out of its parking spot.
And it promotes flocculation, right? The clumping.
Yes, it pulls the clay plates back together, rebuilding those aggregates, which leads to goal number two, improving the physical condition of the soil. Once calcium is back in charge, the soil starts to breathe again. The pores open up.
Okay, so swap the ions, then the structure improves. What's the third goal?
The third goal is enhancing infiltration. We need to be able to wash the enemy away once we've defeated it.
Okay, that makes sense. So let's get into the how. What are the methods? What's the weapon we use?
The undisputed champion, the go-to amendment for sodic soil reclamation is gypsum.
Gypsum, that's calcium sulfate, right?
Yeah.
Place O4 with 2 water molecules.
Correct. This is the first method listed in our notes, and it's by far the most important. It's effective, it's widely available, and it's generally the most cost-effective option. But we need to understand the chemistry. This is prime exam material.
Okay, so let's walk through it.
When you spread gypsum on the soil and add water, it starts to dissolve, releasing calcium ions and sulfate ions into the soil water.
So now we have a flood of free calcium available.
Precisely. And according to a chemical principle called the law of mass action, if you flood the system with one thing, in this case calcium, it will force an equilibrium shift. The sheer abundance of calcium ions forces the sodium ions off the exchange sites. The chemical reaction looks like this. The soil sodium complex reacts with calcium sulfate.
And it becomes a soil calcium complex, and the leftover is sodium sulfate.
You've got it. The calcium takes the seat on the clay, and the now homeless sodium hooks up with the sulfate from the gypsum to form sodium sulfate, which is Na2SO4.
Okay, so we've made the swap. The soil is now calcium dominated. Is the problem solved?
This is the critical step where so many people get it wrong. The answer is no, not yet, because that sodium sulfate is a highly soluble salt. It's just dissolved in the soil water now. What happens if that water evaporates?
The sodium is still there. It could just get back on the exchange sites, or at the very least, you now have a salt problem.
Exactly. You've just traded a sodic problem for a saline problem. So applying gypsum is only step one. It must be followed by the second method listed in our material, leaching.
You have to flush it out.
You have to flush it out. After applying gypsum, you have to apply a large amount of good quality irrigation water. The goal is to wash that soluble sodium sulfate down, down, down deep into the soil profile, below the root zone where it can't do any harm.
And for that to work, you must have good drainage.
Right?
Otherwise, the water has nowhere to go.
Absolutely mandatory. If you don't have a good drainage system, either surface or subsurface, all you're doing is making a toxic soup in your field. So the winning formula is gypsum plus a lot of water plus good drainage.
Gypsum plus water plus drainage. Got it. That's a 3-part solution. What if a farmer can't get their hands on gypsum or it's too expensive? Are there any other options?
There are. Our notes list several chemical alternatives. One of them that's mentioned is lime, which is calcium carbonate, KCO3.
Wait a minute. Lime. But these soils already have a pH of 9 or 10. We use lime to raise the pH of nested soils.
Right.
Why would you ever add it to an already alkaline soil?
That is a very, very sharp observation, and you're right to be skeptical. In general, adding lime to a high pH sodic soil is not very effective. And that's because calcium carbonate is highly insoluble at high pH. It just won't dissolve to release the calcium you need. It would be like adding rocks to your soil.
So why is it even on the list?
It's there as a possibility, perhaps in very specific situations where the soil isn't already full of natural lime, but honestly, it's not the go-to. A much more interesting and clever alternative that's listed is sulfur, elemental sulfur.
Just plain sulfur. How does that help? It doesn't have any calcium in it.
It doesn't. It works through a completely different indirect mechanism. It's a bit of microbial magic.
Huh.
When you add elemental sulfur to the soil, certain bacteria, specifically from the genus Thiobacillus, get to work. They use the sulfur as an energy source, and in the process, they oxidize it to form sulfuric acid.
Whoa, so we're deliberately creating strong acid in the soil.
We are, for a very specific reason. Now here's the clever part. Many of these arid and semi-arid soils where you find acidic conditions naturally contain deposits of calcium carbonate or limestone. That limestone is normally locked up and insoluble.
Ah, I think I see where this is going. The acid you just made reacts with that natural limestone.
Exactly. The sulfuric acid dissolves the native calcium carbonate. And what do you get when you react sulfuric acid with calcium carbonate? You get calcium sulfate, which is gypsum.
That's brilliant. So you're basically using sulfur to manufacture your own gypsum right there inside the soil using the soil's own raw materials.
You are mobilizing the calcium that was already there but was locked up, so sulfur acts as an indirect source of soluble calcium. It's a very elegant solution if the conditions are right.
That is really cool. What about, more organic approaches? I see organic amendments are also on the list.
Yes, and they are incredibly important. We're talking about farmyard manure, FYM, compost, green manures, or industrial byproducts like pressed mud from sugar mills. These are vital for long-term recovery.
How do they help? Is it more of a physical thing or is it chemical?
It's both. Physically, adding all that bulky organic matter helps to improve the soil structure directly. It creates channels, improves aeration, and makes the soil more friable. But there's a chemical benefit too. As all that organic matter decomposes, the soil microbes release a lot of CO2.
Carbon dioxide.
Right. And when CO2 dissolves in soil water, it forms a mild acid called carbonic acid.
And that mild acid, just like the stronger sulfuric acid, can help dissolve some of that native calcium carbonate.
Precisely. It helps to slowly lower the pH and release soluble calcium. Plus, and this is huge, it provides food for the soil ecosystem. It kickstarts the biological activity, which is usually almost dead in a sterile, high pH sodic soil. So really, the best practice is often a combination. A chemical amendment like gypsum for the initial heavy lifting, and organic manures for long-term health and structure.
Okay, so we've amended the soil chemically, we've added organic matter, the land is on the road to recovery. Can we start planting crops now?
Yes, but you have to be smart about it. The next section in our material covers the cropping strategy. You can't just go in and plant a sensitive crop like beans or lentils. You need to start with the tough ones, the tolerant crops. And the number one undisputed champion crop for the initial phase of sodic soil reclamation is rice.
Rice again. It feels like rice is the solution for so many problem soils. But I thought rice was sensitive to salinity.
It is sensitive to salinity, that's true, but it is remarkably tolerant to acidicity, to the high sodium and high pH. More importantly, think about how you grow rice. It requires standing water, a flooded paddy.
And these sodic soils have that terrible infiltration rate, so they hold water on the surface really well.
We turn the soil's greatest weakness into a crop's greatest strength. The impermeability means it's easy to keep the field ponded for the rice. But the benefits go even further. The constant submergence helps leach salts. The rice roots create channels that slowly start to improve vertical drainage for future crops. And the biological activity in a rice paddy, all the algae and decaying roots, generates organic acids, which helps to lower the soil pH over time.
Wow. So the rice isn't just a crop you grow after reclamation, it's an active part of the reclamation process itself.
It's a biological reclamation tool. It's brilliant. After a few seasons of rice, once the pH is dropped and the sodium is lower, then you can start rotating in other moderately tolerant crops, like those mentioned in the notes: wheat, barley, cotton, or sorghum.
So the roadmap is gypsum, then rice, and then gradually diversify as the soil heals.
That is the perfect summary of the strategy.
This is great, but before we move on to the next major topic, I really want to nail down the comparison between sodic and saline soils. The notes have that really helpful table. Can we just run through that quickly?
Absolutely. This is the quick exam comparison, and it's something you should be able to recite in your sleep. Let's do it at the quickfire round. I'll give you the parameter. You tell me the value for a sodic soil. Ready?
Yep, ready.
Okay, parameter 1, EC, electrical conductivity.
For a sodic soil, the EC is less than 4, and I'm remembering that a saline soil would be greater than 4.
Parameter 2, ESP, exchangeable sodium percentage.
For sodic, that's the big one. ESP is greater than 15. Saline soil is less than 15.
Excellent. Parameter 3, pH.
Sodic soil is alkaline, so the pH is high. It's 8.5 to 10.0. A saline soil is usually less than 8.5.
You've got it. And now for the most important one for management, the primary remedy.
For sodic soil, it's the two-step process, gypsum plus leaching. Whereas for a simple saline soil, you just need leaching, no gypsum required.
Fantastic. If you can keep that table straight in your head, you will confidently answer the vast majority of objective questions that try to confuse these two conditions. Sotated means low total salts, but high sodium on the exchange sites, leading to high pH.
Got it. Locked in.
Before we move ahead, here's a quick and important shout out. If you are enjoying this learning session and want more high-quality, concept-based, and exam-oriented agricultural content, make sure to subscribe to Foundation Agri classes. Also, do connect with us on WhatsApp, Instagram, and Telegram, where we regularly share agriculture updates, detailed notes, MCQs, previous year questions, and expert guidance to keep your preparation continuously strong and focused.
I can definitely vouch for the Telegram channel. Those daily quiz questions are a great way to keep the concepts fresh.
They really are. Okay, now I want you to completely reset your brain. We are taking a sharp turn. We're leaving the hot, dry, crusted landscapes of the inland regions, and we're heading to the coast, to the wetlands. We are shifting from sodic soils to our second major topic, acid sulfate soils.
This feels like a complete 180. We just spent all this time talking about soils with a pH of up to 10, and now the name itself tells me we're going to the other extreme.
To the absolute other extreme, we are talking about soils that can become so acidic, their pH can drop to levels similar to battery acid.
That's intense. Okay, let's start with the definition. What makes a soil an acid sulfate soil?
The definition really comes down to two things: its location and its chemistry. Geographically, these are soils you find in coastal wetlands. Think mangrove forests, tidal marshes, brackish water lagoons, and backwaters.
So areas influenced by the sea.
Yes. And chemically, their defining feature is the presence of a specific mineral called pyrite.
Pyrite, that's iron sulfide, right? FeS2.
That's the one. It's famously known as fool's gold. But in the world of soil science, it's not foolish at all. It's a dormant chemical bomb. And this is where our source material makes a really important distinction. It separates them into two types: potential acid sulfate soils and actual acid sulfate soils.
Okay, potential versus actual. What's the difference? Is it just a matter of time?
It's a matter of oxygen. In their natural, undisturbed state, let's picture a mangrove swamp. The soil is permanently waterlogged. It's submerged, so it's anaerobic, meaning there's no oxygen. Under these conditions, the pyrite mineral is stable. It's inert. It just sits there in the soil, not causing any trouble. The pH is usually near neutral, maybe 6 or 7. This is a potential acid sulfate soil.
So it has the potential to become a problem, but it hasn't been triggered yet. The water is acting like a protective blanket.
That's the perfect way to describe it. The water is a lid keeping the oxygen out. But what happens if humans decide to develop that land? Maybe drain it to build a shrimp farm or a coastal resort, or to try and grow upland crops?
You remove the water. And in rushes the air, the oxygen, and that is the trigger. This sets off the chain reaction described in the formation process section of our notes. When that pyrite, FeS2, is suddenly exposed to oxygen and water, it oxidizes rapidly.
And what's the product of that reaction?
The primary product is sulfuric acid, H2SO4.
So we are literally generating industrial-grade acid in the field just by draining it.
That's exactly what's happening. The reaction also produces a lot of iron compounds, which give the soil a distinct rusty red or yellowish mottled color. Sometimes these are called cat clays. But it's the sulfuric acid that's the real monster. It causes the soil pH to plummet, crashing from near neutral down to below 4. Sometimes it can even drop to 3 or 2.5.
And that is an actual acid sulfate soil.
That is when the bomb has gone off. The dragon, as you said earlier, has woken up.
So where in India do we find these? The notes list the geography?
Unsurprisingly, it's all the coastal states. The material lists Kerala, Tamil Nadu, Andhra Pradesh, Odisha, and West Bengal. The Kutanad region of Kerala, which is famous for its below-sea-level farming. Is that a classic example of this?
It is the textbook example in India. Kutanad, with its backwater systems, and the Sundarbans mangrove delta in West Bengal are the two most prominent areas. These are places where you have all the ingredients. The seawater provides the sulfates, the river sediments provide iron, the decaying mangrove vegetation provides the organic matter, and the waterlogged conditions provide the anaerobic environment to cook it all together into pyrite over thousands of years.
Okay, so let's say the land has been drained, the pyrite is oxidized, and now we have a field with a pH of 3.5. What does that actually mean for a plant trying to grow there? What are the specific problems?
The problems are catastrophic. First and most obviously, you have extreme acidity itself. The high concentration of hydrogen ions is directly toxic. It can burn plant roots. But the secondary effects of that low pH are arguably even worse. At a pH below 4, certain elements that are normally solid become highly soluble. The two big ones are aluminum and iron.
Insoluble aluminum is a major plant toxin.
It is incredibly toxic. It's the #1 growth limiting factor in most acid soils worldwide. What it does is it stops root cells from dividing. It prunes the roots chemically. The roots become short, stubby, thick, and brittle. They can't grow and explore the soil for water and nutrients.
And the iron?
You also get iron toxicity, which often shows up on the leaves as a bronzing or scorching effect. But there's another problem. I see you've noticed the P fixation point in the notes.
Yes, phosphorus fixation. What's that about?
It's another classic acid soil issue. All that soluble aluminum and iron in the soil solution act like magnets for any phosphorus that's present. They grab onto the phosphate ions and form highly insoluble compounds like aluminum phosphate or iron phosphate.
So even if you add phosphate fertilizer, the plant can't get it.
The soil locks it up almost instantly. You can pour on fertilizer and the plant will still be starving for phosphorus. It's a huge challenge. And the problems don't stop at agriculture.
The notes mention something really striking: corrosion of concrete and metal structures.
That one data point tells you just how chemically aggressive these soils are. That sulfuric acid will literally eat through concrete foundations, steel pipes, sluice gates. Any infrastructure you try to build in these areas is under constant chemical attack.
That's incredible. This isn't just sour soil. It's a hazardous environment.
It truly is. So given all that, how on earth do you manage it? The objectives are clear. We either have to prevent the oxidation from happening in the first place, or we have to neutralize the acidity after it's formed.
Based on the whole story, preventing oxidation seems like the smartest move.
You are absolutely right. And that brings us to the management practices. The very first method listed is the golden rule, the single most important principle for managing acid sulfate soils.
And what is it?
Water management. Specifically, the recommendation is to keep the soil submerged.
That is the complete and total opposite of what we just learned for sodic soils.
It is the polar opposite, and this is why it is so critically important that you do not confuse the two. For sodic soils, we said drainage is essential to leach the sodium out. For acid sulfate soils, the mantra is do not drain.
Because draining is the trigger. Draining lets the oxygen in, and the pyrite reacts to form acid.
Correct. The absolute best management strategy is to not create the problem in the first place. This means keeping the water table high, always above the layer in the soil where the pyrite is. Keep the bomb underwater where it can't explode. If you can keep the soil saturated, the pH will stay near neutral, and you can farm productively.
But what if it's too late? What if the land has already been drained and it's already an acidic mess?
Then you have no choice but to move to the second method, liming.
Right, adding a basic material like calcium carbonate to neutralize the acid.
Exactly. You apply large quantities of liming material. It could be agricultural lime or dolomite or, as the notes mention, shell lime. In coastal areas, crushed seashells are often a cheap and locally available source of calcium carbonate. The lime reacts with the sulfuric acid, neutralizing it.
And what did that do to the aluminum toxicity problem?
As the lime raises the pH, once it gets above about 5.0 or 5.5, the soluble aluminum precipitates out of the soil solution. It becomes a solid mineral again, where it's no longer toxic to plant roots. So liming is essential to detoxify the soil.
I see leaching is also mentioned here as a method. How does that work in this context?
Leaching is a tool here, but it's a tricky one. The idea is to flush out the acidic water and the dissolved toxic metals after you've applied lime and raised the pH. But, and this is a very big but, you must have access to a good source of fresh water.
Which would be a rare commodity right on the coast.
Exactly. If you try to leach these soils with the easily available brackish or salty water, you're just adding more salts and, critically, more sulfates back into the system, which can just fuel the problem all over again in the long run. So leaching is only an option if you have plenty of rainwater or fresh river water.
And I see organic matter is on the list again.
Yes. Farmyard manure, compost. Organic matter is a great helper here. It has what we call buffering capacity. It acts like a big chemical sponge that can absorb some of the acidity and resist pH changes. And under the anaerobic conditions that we want to maintain, certain microbes involved in decomposition can actually perform a reaction that reduces sulfates, which can help to slowly reverse the acidification process.
Okay, finally, let's talk crops. What can you possibly grow in a soil like this?
Well, we're back to our tried and true friend, rice.
Of course, but for a completely different reason this time, I'm guessing.
A completely different and perfectly complementary reason. In the sodic soils, we grew rice because it tolerated the poor drainage. In acid sulfate soils, we grow rice because it requires the flooded conditions that prevent the problem from occurring in the first place.
So the very act of cultivating paddy rice is the best possible water management strategy.
It is the only major arable cropping system that inherently keeps the soil safe and submerged. The two are a perfect match. Other options mentioned in the notes include very salt-tolerant grasses for pasture, or perhaps the most sustainable option, mangrove-based agroforestry systems.
Which makes total sense. You're working with the native ecosystem, the mangroves, instead of fighting against it.
Exactly. Sometimes the best form of reclamation is actually reestablishing the natural vegetation.
So if I had to summarize the management of acid sulfate soils in one sentence, it would be keep it wet. And if you can't keep it wet, you better be prepared to lime it a lot.
That is a perfect exam-ready summary.
Yes, it's been so helpful. I really feel like I have two distinct pictures in my mind now for these two soil types.
That's the goal. Let's lock in that understanding with one final recap of the whole session. The material gives us some key points to remember. Let's use those to build a final mental checklist, comparing the two scenarios side by side.
Let's do it.
Okay. Scenario number 1. You are standing in a field with sodic soil. Who is the villain? High exchangeable sodium with an ESP greater than 15. What's the environment? An arid or semi-arid region, often with high evaporation. What are the symptoms? A high pH of 8.5 to 10. The soil disperses, feeling sticky when it's wet and forming a hard, impenetrable crust when it's dry. What's the fix? The primary fix is adding gypsum to replace the sodium with calcium. This must be followed by leaching with good water to wash the displaced sodium away. Therefore, good drainage is absolutely mandatory.
Perfect. Okay, scenario number 2. You're now on the coast in an acid sulfate soil. Who is the villain here? The mineral pyrite, FeS2, lurking in the soil. What's the environment? A coastal wetland, a mangrove, a tidal marsh. What are the symptoms? As long as it's wet, it's fine. But upon drainage and exposure to air, the pH crashes to below 4, releasing toxic levels of aluminum. And the fix? The number one rule is water management. Keep it submerged, keep it wet, to prevent that oxidation. If it has already been drained and turned acidic, the fix is heavy application of lime. In this case, drainage is the enemy.
You have absolutely nailed it. That one core distinction. You must drain sodic soils, but you must not drain acid sulfate soils. That is the golden rule. If you remember nothing else, remember that, because it stems from a complete understanding of the chemistry of each problem.
It all makes so much more sense when you trace it back to the why. It's not just a set of random rules to memorize.
That's the entire philosophy of what we do here. It is all cause and effect.
I feel 100 times more confident about facing questions on these topics now. Thank you.
I am so glad to hear that. We've really taken a deep dive today, covering every point in the source material, from the behavior of a single ion on a clay particle, all the way up to the field-level selection of crops like rice.
It's amazing how much detail we were able to unpack.
It really is. So one last time, let's do a final mental flyover. We began with sodic soils, defined by low EC, high ESP, and high pH. We explored the destructive process of dispersion. We identified gypsum as the key amendment for displacing sodium with calcium and stressed the absolute need for leaching and drainage. Then we traveled to the coast to understand acid sulfate soils, defined by pyrite. We learned the difference between potential soils, which are safely submerged, and actual soils, which have been drained, oxidized, and become extremely acidic. And we established that the management priority is the polar opposite. Maintain submergence, avoid drainage, and use lime as a corrective measure.
A fantastic, comprehensive recap.
If you found today's detailed audio learning session helpful, do not forget to subscribe to Foundation Agri classes like this episode and share it with your friends so that more students can benefit from quality agricultural education. Goodbye for now, and keep learning.
Goodbye, everyone, and happy studying.